Alrighty, good morning, good morning. Welcome to homework 9.3. It's going to be a fun one, especially after those difficult regular polygons. So now we're working on composite figures. Nice to have you here. Let's talk about it. Pretty short homework, just one definition and two questions. And so even the classwork's pretty short. So hopefully you enjoy this lesson. It's a bit of a break. It's the last one this week. But let's jump right into it. What do we mean by a composite figure? Well, a composite figure is a combination or a figure that can be broken down into several simpler shapes. So I'm going to even add the word complex figure that can be broken down into several simpler shapes. And by simpler shapes, if we go ahead and give some examples, would be like rectangles, square, I won't say squares, same thing, circles, triangles, and maybe trapezoids. I think you're going to have some problems today with some trapezoids. Okay, so the key is that we take all of our basic area formulas and we can solve kind of unusually shaped figures by breaking them down, because a composite means something made up of smaller pieces, multiple different pieces. And so here's just two quick examples that you could sketch because you're always drawing for your definitions of a composite figure, where again there's no formula for this particular shape. But we can say, okay, I do know some of the shapes within it. And kind of the trick and the skill of this chapter is just kind of quickly finding the simplest way to divide it up, to break it down into several simpler shapes. Now again, there's not necessarily one right way to do this. So sometimes there would be maybe a quicker way. But however you get to it, if you can do it, do it. So for example, this shape here, again, there's lots of ways. I could cut it here. I could cut it here, but what I quickly see is I see two rectangles and a half circle. So again, the way I'm just going to do it is I could cut it off there, because now I have a simple length and width. I'm not going to calculate this. We're just talking through it. So I could find this shape here. Then I could cut this off here, and now I've got a rectangle here, assuming, and a lot of times it depends what numbers they give you, but then I could find these dimensions. And now I've got a semicircle here. And so I could calculate the area of the circle and cut it in half, and I would have that. And then I add those all together, rectangle plus rectangle plus half circle, and I've got my equals my composite figure. Okay? So that's one example. You can have another shape like this, and I do this one because this is the kind of the other way to approach it. It's going to be question 1 right here. As you look at this shape, it's kind of like a basketball court, but with the 3-point circles cut off. You might think, I'm not sure about dividing that into particular shapes, especially since that's a curve. But what we can see is what this actually is a rectangle. Look at what there isn't. We can see that there's a rectangle, and if I calculate the entire rectangle, and then this is a circle, it's just in 2 halves, 1 half, 2 halves. And so if I could take the rectangle and subtract the circles, then what I have left is that unusual shape. So in this case, you might have something where you have a rectangle minus a circle, and that equals the composite figure. So sometimes a composite figure can be found by adding together smaller shapes. Sometimes they can be found by subtracting, looking for the larger shape and then subtracting what I call negative space. Subtracting the negative space. And so that takes us to question number 1, which says, how can you solve a composite figure besides dividing it up into different shapes and adding them together? Here we added them. And the answer is simply reminding you that you can do what we just did here. The other method is you can subtract different shapes. You can subtract different shapes. What I mean thereby is kind of what I'd call negative space. And by negative space, I refer to this area of the semicircle, where if you can see the shape and then you have a larger shape that's beyond the total area, can you find that very easily and then subtract the shape that shouldn't, the extra basically. The circle is extra here. Extra space would be another way we could call this. So just be aware you have both methods. Sometimes you're going to want to add them up. Sometimes you're going to want to subtract them. Then the third thing that they throw at you in this section is irregular shapes. Number 2, how can you calculate the area of irregular shapes? And one, you have to realize it's going to be an estimate. It's not going to be perfect, but that's okay. The second is to divide it up into approximate shapes, just like you would do either of these. Divide into simple shapes and estimate. So if I had something like this that I tried to approximate out of one of the problems in the book, I'd probably go ahead and look at, well, I basically have a triangle here. Okay, and you can see it's not going to be perfect. In fact, it's going to be an underestimate. But I can quickly find the height and the length of this triangle. Then I could say, if I do this, I've got a parallelogram here. And that's just base times height. And then I've got basically a big triangle here. Big triangle here. And so maybe we'll go ahead and just do this one just as an example to show how you would do it. But I have a triangle plus a parallelogram plus then the upside down triangle. Okay? Well, triangles are 1/2 base times height. And so I can see, well, the height is 1, 2. My base is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So my triangle would be 1/2 2 times 6. And whatever I get there, I'm going to add it to my parallelogram. Parallelograms are just base times height. They're just a type of rectangle almost. Or rectangle is a type of parallelogram. So the base is 1, 2, 3, 4, 5, 6 on both sides. 1, 2, 3, 4, 5, 6. That's how I know. And the height is 2. So this is just 6 times 2. And then the upside down triangle, same formula as the one on top, but now I have a base of 6. I already counted that. And the height, the highest point is 1, 2, 3, 4. So 1/2 base 6 times height 4. Alrighty? And you'll have some of these in the book. So now we can calculate that. 2 times 6 is 12. Half of 12 is 6. Plus 2 times 6 is 12. Plus 6 times 4 is 24. Half of 24 is 12. Okay, and so 6 plus 12 plus 12, that's 24 plus 6. Wow, a nice even 30 square. And when you do it on the grid, there's no centimeters or feet, so we'll just say square units. 30 square units. Now I made this. This is actually a problem from the book, so don't worry about where I got this from. You can just sketch the example, but preparing you for how you would do this. And notice some people, when they think of this, they think of, well, I'm going to count the little boxes, and then I'm going to add up all the little halves. You could do that, but looking at a larger shaped area within the irregular, I think that's a lot faster than if we tried to add these all up and see if there's actually 30 boxes inside with all the little halves and fractional pieces. No, create your large shapes. I did a triangle, I did a parallelogram, and then I did another large triangle. And that's probably pretty close to being accurate. Okay, that's it. And it's kind of a nice chapter because it's not adding any formulas or anything. It's just applying simple shape formulas to composite figures by adding them or subtracting them or having them be irregular. So go get it and have a lot of fun.